second mic. Yeah, we got so many devices. I look like a really short version of Batman. All right, so you can just ignore the first portion of the recording, as there's a lot of noise in that first portion. All right, so with the ungraded homework assignment, I'm gonna do that part first, because they do lead to some concepts that we'll be talking about today. So by doing the ungraded assignment, you are studying, you're understanding the symbols, but we are also getting ready for some concepts that we'll be talking about today. So they do serve multiple purposes. Okay, that's good. All right. So we got streaming, we got audio, everything is working. And we'll go back to the class site. And I'm going to show you where it is, okay? In case you missed it, it's okay. We'll go ahead and go back to announcement. It is listed under announcement. So that's your ungraded assignment. I give you the definition of two different sets. Set A has the elements 1, I, 0, 6, 2, B, K. And then set B has the elements of 2, 6, 4, J, K, L, M. Okay? The question now is, okay, tell me all the values that fit this particular requirement. The value has to be in A, and it also has to be in B at the same time. Okay, so let's just kind of go through every single value, and then we'll try to figure out which one will fit this particular requirement. Okay, does this fit the requirement? Why not? It is not in B. Okay, what about this guy? Not in B. This one? Same. This one meets the requirement. How about this one? Meets the requirement. This one does not meet the requirement. This one? Yes. And then this one we have seen already, so we're good. This one we have seen already, we're good. This one we haven't seen yet. Well, anything that we haven't seen yet is not going to fit the bill, right? Okay. So let me just kind of write down the answer on the side, so this way the video recording has the solution as well. So I'm going to use just a notepad tool. Okay, let me resize it so that it fits within the space that we have. And I'll turn off line number because we don't need it in this class. So for the first question, okay, so for the first question, the values that meet the requirement that we just talked about would be 6, 2, B does not meet that requirement, but K does. Is that okay? We only got 3 values that are both in A and in B. Okay? All right. What about the second question? The second question is asking, what is in A but not in B? Now, I know you just heard what I said, okay? But even if I do not say it, you should be able to interpret the mathematical symbol, okay? Because this symbol here means element of, or if you want to say, in a very short way, in, okay? Just in is fine. So this is basically saying x in A, and this is negation or logical negation, which is not, right? So it is not the case that x is in B means x is not in B. So we are looking for values that are in A but not in B. Okay? So once again, we'll go through everything in A and try to answer that question. Is that one of the values? Is 1 in A but not in B? Okay, very good. We just went through this exercise earlier. I would meet that requirement too. It is in A but not in B. 0 is in A but not in B. 6 is in both. So it doesn't meet this requirement anymore. 2 is also in both. So it doesn't meet the requirement. B is in A but not in B. But K is in both. So it doesn't meet that requirement. So when you look at the second question, find all values x such that x is in A and x is not in B. We only got 4 values that will meet that requirement. Are we good so far? All right. So let's look at the third question. So the third question says, okay, I'll let you guys tell me what it means, what it's trying to say. X is in A or x is in B. So we are looking for x only has to be a value that is found in at least one of the 2 sets. Okay? What if it is found in both? It's fine. What if it is found only in A? That's okay. What if it's found in B? That's okay too. Well, that makes this question pretty easy to answer, right? Because we just say, okay, give me everything that is in A. So 1, I, 0, 6, 2, B, K. But also tell me something that is only in B but not in A. Now we don't want to count something twice, okay? Because eventually we want to look at these elements in the form of a set. So we don't want to double count something. So now we look at everything in B. 2 is already counted, so we're good. 6 is already counted, we're good. 4, we haven't counted that yet. Okay, so the list continues on to the next line. The next one is J. Well, J is in B but not in A, so we need to count it here. K is already counted, so we don't want to include it twice. So we got L and then we got M. So we want to double check because this number should be the same as adding everything, the number of items in A plus the items in B minus the number of items that are in both. Because those are the ones that would have been double counted if I just concatenate the items in A and the items in B. Is that making any sense? So let's double check because I am known to make mistakes like that. So let's count. Set A has 1, 2, 3, 4, 5, 6, 7 elements. Set B has 1, 2, 3, 4, 5, 6, 7 elements. So if you just concatenate the list of items in both, then you have 14 items, right? But we know that out of the 14 items, 3 are in both. So 14 minus 3 would be 11. So now we want to look at the answer to the third question and ask, do we have only 11 items here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I did not make a mistake this time. Is that okay? Does everybody understand, the sanity check? It's very simple. It doesn't verify the answer, but it's one way to do a quick check of, whether it makes sense or not. Are we good? All right, cool. Let's look at the fourth question. The fourth question is testing whether you remember implication or not, okay? So if if we have implication, if the first thing, okay, if the thing to the left-hand side of the implication operator is false, the implication is automatically true. So that means the first thing we'll do is to say, well, if x is not in A, that will make it true automatically. So out of all the values that are listed here, we just need to find something, all the things that are not in A. So what is not in A? 4 is not in A. J is not in A. L is not in A. M is not in A. So when x has these particular values, because the left-hand side of the implication is false, then we don't even care about the right-hand side. It doesn't even matter, okay? So now we can focus on things that has to make both the left-hand side and the right-hand side true. Wait, we got that list already, don't we? Out of the answer to question number 1. So now we just have to add those 3, which is 6, 2, and K, and we're all done. Okay, so if x assumes any one of these values, then the expression or the Boolean expression x is in A implies x is in B is true. But this question is super tricky. Yes, go ahead.
So both of them mean false and also makes it true. Do you have to write like a special symbol, like stuff that's not in
No, because that is by the definition of implication. Because when you look at the definition of implication, if the left-hand side is false, the entire thing is going to be true. The implication is going to be true. Is that okay? So now I have to ask you this question. What about m? Oh, m is already here. What about n? The value n. You look at the value n and go like, but n is not even in A nor in B. You're right. N is not in A, and it is also not in B. But when x equals to n, which is a value that is not in A, and it is also not in B, will it make the implication true? Yes. So there's an unlimited number of things that will also make this implication true. If I did not specify, okay, find all values x that is either in A or in B or in both, then the list of things that you have to give me is infinitely long. Because I can say, what about 31? Yeah, 31 would make the implication true because 31 as a value is not in A. That alone makes the implication true. Is that okay? So this is the tricky part, okay? So this is something that you really have to spend some time to wrap your head around because implication is used a lot in this class, okay? This is how we prove theorems. It is the basis of how we do proofs. Are we good so far with question number 4? So we move on to question number 5. Yes?
Can you explain why 6, 2, and k are in the answer?
6, 2, and k, because they are in both. Because if x equal to 6, x is in A is true. But 6 is in B is also true. True implies true also makes the implication itself true. Is that good? Okay. That's a good question. So question number 5. Question number 5 says, something that is in A implies something is in B. Okay? So, excuse me, I just said it wrong. I said implies, but it's not implies. It is if and only if. Okay? So let me say that one more time correctly. X is in A if and only if X is in B. Okay. So how is that different? Well, it's not that different from the first one. In fact, you can look at the first one as a component of the second one. In other words, when I say x is in A if and only if x is in B, it really is saying x is in A implies x is in B, and x is in B implies x is in A. That is basically what it's saying. Because if and only if can be defined by implication and a conjunction. Those are the definitions that we talked about last Wednesday. Yep.
Is that just a fancy way of saying the first one? X is an A and X is
Oh, it's a little bit more than that, okay? But you got one portion of it, okay? So we'll say, okay, when x equal to 6, does it work? Okay, let's figure out. 6 is in A is true, right? 6 is in B is also true because it's coming from the answer of question number 1. So we know 6 is in both. Yes? Okay. So we have true if and only if true. Well, true if and only if true is true. Okay? Not a problem. So that goes along with 2 and k as well. So we'll say 6, 2, and k will all be in this particular, will all meet this requirement. Okay? If I did not restrict the value x to be something in A or in B, okay, now we have to think of all of the other values that I did not even use in the definitions. Let's say 31, okay? So I will propose that 31 would also meet this requirement. And what do you think? 31 is in A is false. 31 is in B is also false. So now the question boils down to false if and only if false. Does that make the if and only if true or false?
true.
It is true, okay? The if and only if operator gives you a value of true when both sides are the same. So they can both be true, they can both be false, but either one will make the if and only if true. So once again, just like question number 4, if I did not place a restriction, now your list is infinitely long because there's an infinite number of values that is in neither of the sets. Do we have any questions? Because if you have any questions, now is a good time to ask. Yes?
So then how do we include the infinite number? Do we just put an empty set or put any time?
Well, you can do something like this. You can say, and everything else except for. Okay? So let's do it like this. Okay? And everything else except for. Okay? Except for what? Except for things that are in one but not the other. Okay? Now, is that list somewhat small? It is kind of somewhat small because you just take these 3 elements out of A, the rest goes on to that list, right? You look at everything in B, you take out these 3, that also goes on that list. So let me be complete here. So just to kind of finish the list, except for 1, I, 0, 6 is already here, fine, 2, K, then we got B, right? And then we have, let's see, 2, 6, then we have 4, then we have J, K, and then L, and M. So I think that is correct. Yep. Yep.
Explain the qualifications for question 4 for values not in set A and B again, like 31.
So question number 4 would also kind of need this kind of statement. Yeah, so it will also need something like that to be complete. So this one, and it will say, and everything else except for, but this time the except for is not the same as question number 5 because this is an implication. In other words, we just need to exclude things that are in A but not in B. Okay, that needs to be explicitly listed and say, we'll include everything, the kitchen sink, okay, your pet, and everything else, except for these guys. These guys cannot meet that requirement. So what would that be? We already have seen all the things that are in A but not in B. It is in the question number 2. So except for 1, I, 0, and B. But somebody's going to say, well, what happens if it is 1? What if x equals to 1? Okay, so let's plug it in and figure out, right? So we'll plug it in and say, what if x equals to 1? 1 is in A is true. 1 is in B is false. Okay, so we know the 2 sides of the implication. Now the question is, what does that make the implication itself? We have true implies false. The implication itself is false. Okay, so that is why we have to say, nope, these guys would not meet the requirement. Everybody else does. Is that okay? All right? Yes?
So false can imply true because it doesn't disprove it? Is that right?
Yes. So it depends on how you look at this. Okay, so the way you want to look at it is whichever way makes more sense to you and more clear to you. Okay, so you can look at it from the perspective of what I said in the previous class. I told you something. If A then B, right? But that statement only says something about what would happen when A is affirmed. When A is known to be true, then B is going to follow, right? I didn't say anything about what if A is false. Okay, so when A is false, then no matter what happens, the implication itself is still true. So you can look at it from that perspective, which is based on the semantics of if then, okay, or something implies something, or A is sufficient for B. Okay, those are all different ways to say exactly the same thing. But there's another way to look at it. Okay, if you want to look at it from the logic perspective, A implies B is really saying exactly the same thing, okay, as not A or B. Now I'm starting to use the alternative symbols that I mentioned in the previous class on Wednesday. So if this looks weird to you, that means you need to do some studying. Because this is already covered. It's already mentioned that I would use plus in place of disjunction, and I would use multiplication in place of conjunction. But I choose to kind of stick with exclamation point for negation because it's easy to type. Is that okay? So, all of this stuff here is really kind of a quick test of whether you did some studying or not, whether you retain what we talked about last Wednesday or not. If you're not retaining, okay, it's okay. We are not quite that close to the first exam yet. Just have to do some studying. So are we good so far with the ungraded assignment? Okay, yep. Well, if you do not, then I will ask you, what about 31, right? So unless the question says, okay, limited to only the values mentioned in this question, then you don't have to say everything else except for blah, blah, blah. But if I did not say that, then in an exam, you probably want to clarify with me, okay? Yes?
Everything else except for the first part.
Yeah, so if you include and everything else except, then you don't need 6, 2, and k. But including 6, 2, and k would not make it wrong either, right? Well, okay, if you do not list 6, 2, and k, then you don't want to use the word else, because you would just say everything except for these. But if you explicitly list 6, 2, and k, then you have to say everything else, because we don't want to double count stuff. Are we good so far? All right. All right, so let's go ahead and look at the topics that we are in at this point. So we have already talked about basic set theory, which talks about the very basic symbols. An element of, right? That's one of the things that we talked about. So let's just go there because, I just want you to know where the notes is and what it looks like. Okay. So we already talked about, the element of, symbol. Okay. But the rest we haven't really talked about. So section 3 has to do with, well, if I have set A and set B, okay, not the ones that we have seen, okay? If you give me two different sets, the question is, how do I know these two are the same? How is the equivalency established? So I'll just go ahead and read the sentences. A set can be compared to another set to see if they are the same. Okay, not too surprising. At this point, we lack the precise mathematical notation for this kind of discussion, but we can still just use natural language for that, okay? Because to really define this, we really need for all, and there exists the quantifiers, okay? And that's why you see quantify as the next topic. So let's say we're interested in whether set S and T are the same. The two sets are considered the same when every element in S is also in T, and every element in T is also in S. Are we good so far? That sounds pretty reasonable, right? So you have a collection of marbles, I have a collection of marbles, and then the question is, do we have the same kind of collection? Can a third person comes in and go like, yeah, you two have the same collection of marbles. Okay, that's kind of the question. So you kind of have to make sure that whatever marble you have, I also have. Whatever marbles I have, you also have. If that is true, well, just from common sense perspective, you can kind of say that the marble collections are the same. Are we good so far? But marbles can only get you so far, because you cannot have a marble in a marble. But you can have a set in a set, okay? So the next thing talks about, What do we do when we have a set that is an element of another set? That sounds really confusing, doesn't it? Okay, because a set contains values, right? It by itself is a collection. Can we have a collection of collections?
A two-dimensional array, I think.
Oh, it's easier than that. It doesn't even need to get to arrays. If you know how to find files inside the file manager, you have been exposed to this concept already. Because a set is really just like a folder. It can contain nothing, right? You can create an empty folder in which there's nothing. Are we good? So you look at C:\\, which is the root folder of your C drive, right? And in it, you got individual files, a whole bunch of that, that kind of stuff. But you also have folders. So now you do have a folder in a folder. Does anyone in this class feel kind of awkward that you can have a folder in a folder? Good. Because I was just about to say, well, computer science may not be the best choice. If a person feels, I'm really not okay with the concept of a folder in a folder. If you're good with that concept, why not a set in a set? Is that okay? All right. All right. So we'll work with section 4 a little bit. So to quantify as a potential element, a value must be comparable to other values to determine whether they are the same or not. Okay. Now this is really crucial because you have to be able to take one element from one set, take another element, take an element from a different set, and compare and say, are they the same? Okay, because that's the fundamental mechanism to establish whether two sets are the same or not. Is that okay? So what if I pick out one set as an element from one set, and then I pick out another set from the second one? Can I compare a set to a set? We just mentioned it, right? So that means we just have to apply that method starting with the R. Recursively. Okay? All right. So that is kind of summarized as follows. In general, given two values, x and y, okay, I pick x from one set, I pick y from the other set. Knowing that x is a set, this is how we can determine whether x and y are the same. The first thing is x and y, because we know x is a set already. Yes, that's a given. Y has to be a set. Otherwise, x equals y is got to be false. Does that make sense to you? Okay. Somebody has a bag of marbles. Somebody has a single marble. Can I say that one single marble is equivalent to a bag of marbles? No, I don't even have to look into the bag because the single marble is not in the container. Okay? So if y is also a set, then we can use the set comparison method. Yeah, I know, I made a label and then I probably used the wrong label here. In section 3, to determine whether x equals to y, we just apply that method recursively. Is that okay? Because section 3 talks about how do we know two sets are the same. Now we have set x, we have set y. I want to know whether they are the same or not. So apply the algorithm recursively. Are we doing okay so far? Yes? Okay. Now, let's go back to section 3 a little bit. So because this is kind of like a loose definition, we say, if everything in S should be also in T, everything in T has to be in S, then S and T are considered the same. What if they're both empty sets? What if S is empty, T is also empty? Are they the same? They are the same. Okay, very good. So you're correct. So instinctively, you guys already know that two empty sets are considered equivalent. Okay, it's kind of like you have an empty marble bag, and I have an empty marble bag. From the third person's perspective, Are they the same? They are the same. They're both empty. There's nothing. Very good. So note that now that we can compare a set with anything for equality, it is not surprising that a set can be an element of another set. So we can have X being A, B, and then as a set 1, 2, 3, is a set that has one of its elements being a set itself. In other words, we look at this portion of X and say the set 1, 2, 3 is an element of X. Okay? I know some of you know the term subset. It is not the right word to use here. The set of 1, 2, 3 is not a subset of X the way it is defined. It is an element of X. Is that okay? All right. So we'll get to the subset notation later, but I just want to point out, if you in your mind says, oh, but it's a subset. No, it is not a subset. Yes?
So if the set itself is considered to be an element of X, are the values inside also considered to be an element of X?
No.
1 and 3, no?
No. So in this case, the value 1 is not an element of X, but it is an element of X. Yes?
So basically, if you took out the curly brackets from the top one, then the statement would be false.
If I take out
If you were to take that out, if
this
it
one
wasn't- if
and
it
this one,
wasn't- if it wasn't listed as a set right there, then would that statement then be false?
well, okay, let me kind of give you this one, because I can do it on the side right here. So given that X, okay, so I'm just repeating the definition here so it does not appear out of context, okay? AB in X is false. 1, 2, 3 in X is true. Does that answer your question? Okay. Because the set that contains AB is really not inside the curly braces that encloses all the things in X, right? But 1, 2, 3 as a set is definitely here. Yep.
What if one set has like 4 empty spaces, and the rest of the set is exactly the same as another set that's totally full?
Empty spaces. So are you talking about something like this? What do you mean by empty space?
It's like when you make an array and you just have it empty, but you specify the size of like 10, and then you have another array that's size like 5. They're both empty. Would they be the same?
Okay, so let's go back to that statement. An array that has 3 elements is not empty. It has got 3 elements. It has got 3 things in the array. Now, each thing in an array, now it depends on which programming language you're talking about. But in C and C++, which are strongly typed programming languages, okay? So now it depends on, is it an array of integers? Okay, so let's say it's an array of integers. So an array of 3 integers can never be empty, because each integer that's a part of that particular array has a value. So it's not really empty. An empty array is an array that has no elements. Now, you can make an array that has no elements using new in C++ or using malloc in C, but typically those arrays really have no reason to exist. Is that making any sense? Okay. So any other questions? Yep.
I think what they were trying to get at is like if it was a set of empty sets.
Okay. Okay. So let me just regurgitate what you said. A set of empty sets. Well, that by itself cannot exist, because you cannot have duplicate values. No 2 elements of one set can be considered the same. So that means this is not a valid set, because an empty set, as we already talked about earlier, is equivalent to an empty set. So now we have 2 elements in the outer set that are considered equivalent. So that breaks one of the rules of what a set can contain. It cannot contain duplicate items. So the answer is you can have a set that has an empty set in it. That's fine. But if you guys like curly braces and really want to say, but I really want to put something that has empty sets in it again and not to count it as bad, okay? Well, you can do it like this. And so on. That's totally okay. Now, why is it okay? Because they are different. They're considered different. So I look at this element, okay, and I ask, is it equivalent to this element? Well, not at first glance, okay, because at first glance, they are both sets. So now we need to make sure whatever is in one is also in the other one. Whatever is in the other one is also in the first one, right? Okay. So we look at this set here and say, you got nothing in it. Okay. We look at this set here and go like, you got one thing in it, right? Because it has got an empty set in it. And we go like, well, the other guy, do you have an empty set in you? Going back to this guy says, nope, I got nothing. Aha. So one set has an empty set as an element. The other set has nothing in it. They are not the same. Is that okay? So you can kind of imagine that we can make more of these things where you have a set that has a single set, that has a single set, that has a single set of an empty set. You can have this. I mean, this is a valid set. This is a valid set. You know, it can exist. So go ahead and then to you.
Right.
Yep.
Going back to the statement of A and B and X is false, it's only false because it's not including the set of 1, 2, 3, right?
You mean here?
That statement is,
This one?
Yeah, that statement says
Okay.
A and B in X is false, even though A and B is an X, but since it's not including the set of 1, 2, 3, that's why.
The set of AB is not existing as an element on its own in X. Yep.
And so they have to have the same number of elements in them, right, to be equivalent, two sets?
Now, that is a very interesting question, because what if they are both sets that has an infinite number of elements? Now, I'm fast forwarding a little bit to concepts that we'll be talking about, but counting elements is not going to work when you have two sets and each one has an infinite number of elements.
Okay, and then
So you still have to kind of go back to the first definition. If an element is in A, is it also in B? If an element is B, is it also in A? So the two sets are the same if and only if something is in A, if and only if that something is also in B.
the order doesn't matter, right?
Order does not matter because in a set there's no ordering. Is that okay? All right. Shall we move on? Are we sufficiently confused? Not yet. Okay, we'll get to that point. That's my job. Okay. So now we move on to section 5. Guess what? We are now getting into sets that have an infinite number of elements. Well, at this point, our concern is only how do we tell people what is inside a set when a set has an infinite number of elements. So in here, okay, you can list by examples. For instance, I want to tell you that E is a set of even integers. Okay, well, there's an infinite number of integers that are even because any integer that is divisible by 2 is even. And there's an infinite number of those. So how do I convey that message? I can kind of give you an idea like this, but there's really no guarantee that the next one is going to be -6, right? The next one can be -8, and then the next one after this can be 8. So this is not a very foolproof method of telling people what is in a set. Yep.
If a set's infinite, does that mean it has everything in it then? Because it can't
No.
be duplicated, can't have
No. Let me give you a counter example, okay? Let's consider the set of all the odd numbers. How many odd numbers do we have? an infinite number, right? And then we consider another set, which is the set of all the even numbers. Well, those two together, I mean, first of all, they do not have any common elements, right? Because a number cannot be odd and even at the same time. Yes? So even if you were to put those two sets together, what about pi? Pi doesn't fit into any one of those two because pi is not an integer. So no. So you can have all kinds of sets that have an infinite number of elements, and whether they span, everything or not, that's a whole different question.
So some can have parameters or some can have parameters or a set of instructions of what they can and cannot have.
Yeah, we need a qualifier. Okay, we need some kind of qualification of if you meet this requirement or if you pass this test, you are a part of this set. Okay, which is kind of what we'll talk about next. So perfect timing there. Okay. So this part here is a notation. Okay, so we'll focus on this particular definition. It's trying to define the same thing. Okay, it's trying to define a set of all the even integers. So this notation is saying, each element of this set is x such that. Okay, so the vertical bar, a single vertical bar, can be seen as such as. Okay, such that. Okay, not such as, such that. Okay, such that x is an element of this symbol means the set of all integers. Okay, I have no idea why it is a z, probably a Greek symbol, not an English symbol, probably zeta. So z, x is in z, and x mod 2 equals to 0. Now whether you want to kind of say x is an integer or not, probably is not needed, because 1.5 mod 2 is not going to be 0. Is that okay? Is that making any sense? So this way we are spelling out a test and say, give me a value, okay? Okay, I'll give you pi, okay? 3.1415, blah, 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 blah. Plug it into this x here and see if this test will give me a true or a false. So the first part of this conjunction says, well, x has to be an integer. Ah, darn it, pi is not. Okay? If one side of a conjunction is false, the entire conjunction is false. So now we know pi is not a part of this set E. Give me another number, 26. Okay? I plug in 26 into x and see if the conjunction is true or not. Is 26 an integer? Yeah, it's an integer. 26 mod 2 equal to 0. Is that true or false? It's true. So we got true and true, which means 26 is an element of E. Is that okay? What about 25? Is 25 an integer? Yes. What about 25 mod 2? 25 mod 2 has a result of 1. 1 equals to 0 is false. So the conjunction says true and false, which is false. So if the whole expression evaluates to false, that means 25 is not in this particular set. Yep.
Isn't the first part of the statement kind of unnecessary? Because if it's not an integer, then x mod 2 is not going to equal 0, right?
Well, but if I don't use that first, then you can give me something that is not a number, and a number I cannot apply mod to a number. So it's kind of a guard condition so that the second expression makes sense. But you're correct. From the strictest sense, that is correct. Because somebody may give me, in this case, it'll give me something that is not a numerical value, or can give me a vector, right? So you can ask, what is a vector mod 2? Well, are you modding every single element in the vector and making a new vector? How do you mod 2 with a vector? So that operation is not defined. So that's why the first one is only here as a guard condition. If it doesn't meet the first requirement, don't bother with the second one. All right. Are we okay so far with the shorthand? Yep.
Sorry, isn't that a line right after x that is such that, or
Yes. This bar here is such that.
is it the same as if and only if?
Yeah. So something is in E if and only if that something makes this true. Yep. So I think that's mentioned somewhere in the notes too. So it is if and only if. Yeah, I actually mentioned if and only if. Yep. So are we okay so far? So I'm gonna say, okay, we'll condense this part or abstract this part here, the part that is highlighted at this point, to what we call a predicate. Okay, predicate is just a fancy word. Okay, from your perspective, because all of you have taken C++ already, a predicate is a function that returns a Boolean. Okay, it takes at least one parameter and it returns a Boolean. Is that okay? So every time I say predicate, what do you think about? A function that returns a Boolean. And usually it's parameterized, okay, has at least one parameter. So I'm gonna just kind of make it shorter. So in this case, if I define E this way, x such that P of x is true, okay, that means if x is an element of E, okay, I shouldn't say if, x is an element of E if and only if P of x is true. That's basically what it's saying. So it's really just a shorthand. In other words, if you look at this equivalence and you look at this, if and only if, they're telling you exactly the same thing. They're both trying to define what set E is, just in slightly different ways. Is that okay? Most mathematicians prefer this way, but it really is just spelling out that. Are we good so far with this notation? All right. Yeah.
So the predicate can be anything as long as it's defined beforehand?
As long as the definition of the predicate returns a Boolean value, it's good. Yep. Are we good? All right. So moving on. So section 6 talks about the empty set, a set that has no elements. There are different ways to draw it. I think one way is to draw a circle and then a bar across it. That's another notation of an empty set. But in this class, I just used a open and then a closed curly brace because I think that's actually the most intuitive way to visualize an empty set. Okay, here's the delimiter and here's the other delimiter, and there's nothing in between. Okay, so that's how I'm gonna represent empty set in this class. All right, section 7. Now, section 7, are operators. Some of these will return a set. Okay, so the operator itself will take one set on one side, it will take another set on the other side, and then it will give you back a set as a result. Okay, so the first one is just like that. Okay, this is intersection. So A intersecting with B will give you a set. So it can potentially give you a set that is neither A nor B, okay? Potentially. So what is the definition of A intersect with B? This is how we spell it out. An element E or value E is in A intersect with B if and only if it is found in A and in B. That's it. So did we work on an example of finding the intersection of two sets today? Like way back, right? The first thing we did was that. That's why I said, the ungraded homework assignment is not only, helping you to reinforce what you learned last week, but it's also going to help you to learn what we are going to introduce today. So are we good? Okay. Are we okay with intersection? Okay. The next one is union. Okay, so this is union. So A union with B is written this way, A, and then it looks like a U, but it's not exactly a U, B. Okay. An element is in A union with B if and only if the element is in A or the element is in B. So in this case, it's very important to not to say either. Okay? Do not say either, because if you say either, that means if it's in both, then it's not going to be counted. Is that okay? So we just want to say or, not either or. Did we work on an example like that earlier? I think it's question 3. Okay, question 3 of the ungraded assignment, is really working out something like this. Cool. Then we have difference. Okay, it looks like subtraction, but it's not really subtraction. Okay, so how is it defined? A minus B itself is a set. Now, how do we know A minus B is a set? Just from notation perspective. The curly brace. Okay, whenever you see open curly brace and end curly brace, they are delimiters of what is in a set. Okay, so A minus B has a result that is a set. What is in this set? A value E is in the set of A minus B if and only if the element E or the value E is found in A and it is not found in B. Wait, that sounds awfully familiar, because question 2 is correlating with this. Are we good so far? So difference is found in the first one, but not found in the second one. Are we good? All right. And there's not a whole lot remaining. So this is Cartesian product. Okay, Cartesian product is a little funky. Okay, really funky. Because when you have a set A and you have a set B, the Cartesian product is not even going to give you elements that is either in A or in B, or in A or in B, or in A and in B. Elements in A Cartesian product with B is not in A nor in B. Then you go like, what is going on? Well, that's because each element of the Cartesian product is known as a 2-tuple. Now, if you have taken 430 already, or you're familiar with the concept of an array or the concept of a list, that's basically what a tuple is. So a tuple in this case, you can see this as an array of 2 items. What about these 2 items? The first item comes from A. The second item comes from B. Is that okay? I think this one needs an example. So we'll go ahead and take a look at a quick example here. Okay, so I will work with something that's relatively simple first. So let's say the first set has lowercase ab as its elements. The second set has numbers, okay, 1, 2, as its elements. So the result, the Cartesian product, is a set, okay? We know that. But we also know it is a set of tuples. Now, tuples are different from set. The set notation uses curly braces. Things that are inside a set, the order is not important, okay? And you cannot have duplicate items. A tuple is no more than just an array or a list. So things can appear multiple times. The same value can appear multiple times in a tuple. And ordering is also important, okay? So the tuple of 1, 2 is not the same as the tuple of 2, 1. And you can have a tuple of 1, 1, because in a tuple, values can duplicate. You can have repetitions of values. So this is an element of that particular set, because the first item of the 2-tuple comes from the first set, the second item comes from the second set, so that makes it a valid or a legitimate element of the Cartesian product. So the next one, it kind of depends on how you usually want to cross product things, but this is one way to list it. Is that okay? if you look at every single element in the Cartesian product, you take the first item of each two tuple, it has to be an element of the first set. And if you look at the second item, it has to be an element of the second set. Is that okay? All right. Well, if this is okay, can we have something like this? Okay, we have 1, 2 as a set, and we Cartesian product with itself. Can that work? And the answer is absolutely. You have 1, 1, 1, 2, 2, 1, and 2, 2. Wait, that looks like a graph. Looks like things on a graph paper. And you'll be right. Cartesian product. Exactly. So one spells out all the values on the x-axis, the other one spells out all the possible values on the y-axis, and then you have all the coordinates that are possible, but they have to be on a grid because they're all integers. So are we good with the concept of the Cartesian product? Okay, if you have taken linear algebra, it's kind of like spanning, the concept of spanning a space, okay? But it's not exactly, okay? Because the difference between linear algebra and in this class is in linear algebra, it is continuous. Okay, if you have two vectors that are not aligned, okay, they can span a plane. But the plane is continuous, it's not individual dots. But in this class, it is called discrete math for a reason, because things are individual. Okay, it's not continuous. So that makes this class different from your calculus classes, from your linear algebra class, because things that we deal with in this class are not continuous. Are we good so far with Cartesian product? Yes? Okay. So now we start with other things, other operators. This is an operator, okay? A is a subset of, okay? But these operators, it will take one set on one side, it will take another set on the other side, but the value that it returns is Boolean. It's either true or false. In other words, if you just look at A is a subset of B, that can be true, it can be false, because it just gives you a Boolean value. Is that okay? All right. So the definition of subset of is A is a subset of B if and only if the difference between the two is empty. Or I should say, if you look at everything in A that are not in B, it has to be an empty set. Wait, there's another way to say that, isn't there? Let me say that one more time, and then you guys can tell me whether there's a more elegant way to say it. Okay, so by definition, A minus B is telling me what is in A but not in B. Okay? Equals to empty set means everything in A, everything in B has to be in A. Okay? That makes A a subset of B. Okay, hold on a second. Everything in B, everything in A has to be in B. Yep, that makes sense. Yep. Because the minus sign says everything, things that meet this requirement, they have to be in A, but they cannot in B. So if you look at everything that is in A but not in B, there can be nothing. That means everything in A has to be in B. Yep.
Which one's the subset?
A is the subset. A is the smaller one. Yep.
So B just contains A.
Now you have to be careful with that word, and that's why we don't use that word contain, because contain can be associated with subset of, can also be associated with element of. So we don't say contain, okay? We say subset of or in. Okay, so we can use an example, okay? So in this case, it's pretty easy. So we can say 1, 2 is a subset of 1, 2, 3. Does that make sense? You look at 1, 2 and you look at 1, 2, 3. what is 1, 2 minus 1, 2, 3? In other words, I'm asking, what are the elements, what are the values that are found in A but not in B? A is, 1 is in both, 2 is also in both. I cannot find anything that is only in A but not in B. So A in this case, which is 1, 2, is a subset of 1, 2, 3. Wait, hold on a second here. But doesn't that mean every set is its own subset? So let's check this out. Okay, we got 1, 2, 3 is a subset of 1, 2, 3. Is that true? Using the definition that we just mentioned, is that true? 1, 2, 3 as a set is its own subset. Well, look at this requirement. Okay, A is a subset of B if and only if A minus B is an empty set, or everything in A can also be found in B. Is everything in 1, 2, 3 found in 1, 2, 3? Yeah. That meets that requirement. So that means every set is its own subset. Yep.
So, layman's terms, if you take everything that's in B and you subtract that from A and you get an empty set, that makes it true?
You take everything in B and then you take away things that are in A. I think it's the other way around. You take everything in A and then you remove the ones that you can also find in B. If what is left is an empty set, then you have A being a subset of B. Yep. Mm-hmm.
So, for B, the 1, 2, 3 set, what if instead of 1 and 2 being second elements, it was a set within a set?
If you have a set within a set,
So,
so tell me what we are working with.
so it's the set 1, 2.
Set 1, 2.
Set 1, 2 is a subset of set 1, 2.
Oh, and then a 3 like that. Okay, well let's check this out, right? Okay, so the question now is, so let's go back to the definition. Let's look at 1, 2 minus 1, 2, and then a 3. Okay. So, well, we just have to look at everything that is in 1, 2, each one, and ask, is it also in B, right? So let's focus on one at a time. I'm only focusing on this of A, okay? And I'm asking, can I find this in B? Is that also an element of the other set? No. Okay. So that means the difference is going to be non-empty to begin with. We got at least one in the difference. So that means it is not a subset of. Okay? So this is actually a very good example because I can now say is a subset of is false. It is not. Okay? But, okay? That one is true. So the word contain doesn't quite convey. Are we thinking about 1, 2 as a set as an element, or are we looking at 1, 2 as a subset? Okay, so that's why we don't use the word contain, because it's neither in or element of or subset of. So is that okay? Is everybody understanding why 1, 2 as a set is a subset of the set of 1, 2 as a set, comma 3 is actually false? Because 1 as a value cannot be considered the same as 1, 2 as a set. Are we good so far? All right. So these are kind of the trickier cases, okay? And that's kind of important, okay? Because if you can get all the trickier cases, then you probably understand the concept already. Are we good? So now we are defining another operator, which is very related to the first one, which is a proper subset of, okay? And you can see the only difference between the symbol is that bar is gone. Kind of like less than or equal to versus less than, right? So let's take a look at the definition, or one of the definitions of A is a proper subset of B. A is a proper subset of B if and only if A is a subset of B and there's something in B but not in A. So B has at least one extra thing compared to A. Kind of makes sense, right? Because if you just look at subset of, a set is always a subset of itself, okay? But when you look at proper subset of, then a set cannot be a proper subset of itself, because a set can only be a proper subset of something else that has at least one additional element. Yes?
Does that mean the same thing as if just the two sets are equivalent to each other? How is two sets being equivalent to each other different in this case than B minus A not being a negative set?
Well, if two sets are equivalent to each other, there are many ways to spell it out. So if A and B are the same, that means A is a subset of B and B is a subset of A. Yes. Yeah.
But they're not proper subsets.
But not, yeah, exactly.
Right, okay.
Just subset of, but not proper subset of.
Okay, I think I got it.
Okay. So I'll just write it out too. So I'm just going to write here, A is equivalent to B if and only if A is a subset of B and B is a subset of A. But that's a very roundabout and long way to define equivalency. But if two sets are the same, it would meet the requirement. They are subsets of each other. Are we okay so far? Okay, all right, cool. And the last one is called the cardinality. Okay, that's a super fancy term for how many things are there, okay? So the notation, I borrowed the notation of bar, which most of you know as absolute value, okay? So when you see bar and bar, it does not mean absolute value in this class. It means what is the cardinality of a particular set. The cardinality is a fancy word of how many things are in a particular set. That's it, you're just counting. So when we look at this particular set, 2, 4, 6, 8, it has 4 elements. So the cardinality of 2, 4, 6, 8 as a set is 4. You're literally just counting. Okay? And I know some of you is already thinking, but Tech, you mentioned a whole lot of stuff about sets that have an infinite number of elements. So now the question is, how do we can we even compare them? Because you cannot compare infinity to infinity, right? Okay, so this is a little preview of things that we'll talk about. Okay, so let's just say that E is a set of all even numbers. Okay, so I'm just gonna spell it out in English here. Set of all even numbers, or to be more specific, even integers. Okay, and then O is the set of all odd integers. Okay, is that okay? So now the question is, can we compare? Oh, let's make one more. Okay, R is the set of all real numbers. Okay, are we good? You look at these 3 sets and you go like, okay, they all have an infinite number of elements, right? Because you can give me the largest odd number, and I'll ask you, what about that plus 2? Right? And the same thing for even numbers, okay? And we also know that there are an infinite number of real numbers. Okay, so now the question is, can we even compare the cardinality in this case? Because in your math classes, in calculus, they say that infinity cannot be compared to infinity. You cannot look at which one is larger. Right? Okay. But we can actually say something like this. We can say this actually does equal to that. And then we can say that this does not equal to that. Whoa, hold on a second here. That means we can compare infinite numbers? Well, as it turns out, the equivalency of cardinality is not done by counting, okay? It's done by mapping. Okay, the question is, okay, now this is something that is also a preview of something that we'll talk about later, but if you can remember the context, okay, you're just linking, you have more linkages between concepts of this class, which means, it's easier for you to study, okay? The more, how should I say it? The more connectivity in your mesh of concepts, the more you're understanding the material. So the way we establish this equivalency is, do we have a one-to-one mapping between elements of this to elements of that? That's basically what it's asking. So it is basically saying there's no one-to-one mapping between these two. The set of all even numbers or even integers versus the set of all real numbers. I cannot create a one-to-one mapping between those two. On the other hand, if it's odd and even number, I can actually create a mapping. So go ahead.
If that's the case, can you establish that one set is greater than another in terms of infinity?
That I do not know. Okay, I do not know, because you can only, as far as I know, is you can only say that you cannot find a one-to-one mapping or a bijective function, which is one of the concepts that we'll talk about in this class, is you cannot find a bijective function between those two sets. Yep. So if that thing does not exist, they are not equivalent. But when they're not equivalent, you cannot just say that one is larger than the other one. Now, it is true in this case that when you look at real numbers, now real numbers are interesting because you can keep subdividing. So even if I just limit the range of real numbers between 0 and 1, you still have an infinite number of real numbers between that range, and I will still not be able to do a mapping to the set of all integers. Yep.
I'm just still a little confused by what you mean by the mapping.
We'll talk about the mapping thing later. It's basically what we call a bijective function. So a bijective function, I can give you a quick preview. A bijective function is a function that has a reverse, has an inverse function. It's inversible or reversible. Because not all functions are reversible, which means you can send values to the other direction, but once you get to the other direction, you cannot reverse back to a single value from where you start. Okay? But on the other hand, if you have a bijective function, it goes both ways. Each value on this side maps to one and only one value on the other side. But if you know what value is mapped to, you can always know which value is mapping to that value. It's reversible. So we'll spend quite a bit of time to talk about functions, injective, surjective, and then bijective. The notes is already online, so for those of you who are curious, you can always read ahead of me because I just introduced the concepts in that particular sequence. I know we are running out of time, but I do want to show you where we are in the notes. So we are finishing up basic set theory. You should read ahead of me before Wednesday. At least get started with quantifiers. Okay, I think we can finish the entire quantifier discussion on Wednesday, and then we'll get back to set theory because we want to utilize quantifiers to kind of redefine some of the operators. Okay, so that way we have some practice of using quantifiers, and then we have another way to look at the set operators. This is a test or a quiz. I haven't really assigned it yet. Just in case you guys haven't noticed, is a 2019 date, so it has not been assigned. Don't worry. Okay, we'll only start with this one when all 3 topics are done, and then the next block of topics are functions. So if you can read ahead of me as much as possible, I think that's to your benefit. Okay? Yes. Ungraded assignment. Another one? Yeah, I can do that. Yep. I have to think about it, but I can work on that a little bit. If you don't get anything by tonight, just kind of nudge me, send me an email.
Yeah, sure. I think I still have yours, but
Just for verbal clarification.